All right, good morning. We're going to continue on today with Chapter 4. This is Professor Grenfell's continuing lecture series on Math 12 Statistics for Riverside City College. And like I mentioned, we're continuing on in Chapter 4, Section 1. We're going to be going over briefly probability rules. So the probability of any event, let's call it E, is some number between 0 and 1 inclusive. So here, we'll say it like this. P, and then parentheses, E inside, we read that. That is function notation, so we would read that as P of E, the probability of this event, E, occurring. So that's the significance of this notation, P of E. And then it is between 0 and 1, and it is allowed to be equal to 0, and it is allowed to be equal to 1. All right, so that's the first thing. The second thing, the sum of all of the probabilities of all of the outcomes in a sample space has to add up to a total of 1 as well. If an event cannot occur, it is impossible, or in other words, that event is not in the sample space, then its probability is 0. And then finally, if an event is certain, then its probability is 1. Okay, so let's take a look. Here is example 4-8, and it says, when a single die is rolled, find the probability of getting a 9. So here, we're going to roll a single, and we're assuming that it's a 6-sided dice, regular 6-sided dice. Roll a single die. What is the probability of getting a 9? Well, there's two different ways to think about this. They're, essentially equivalent, but it wouldn't really be redundant to say both of them. The first way to address this probability, let's call it like this: P of 9, right? Probability of an outcome of 9. This would be 0. Because it's impossible to get a 9. Right? The other way to see this is the number of outcomes that satisfy this event is 0, because 9 is not in the sample space, divided by the number of events total, the number of outcomes total in our whole sample space. So these are 1, 2, 3, 4, 5, 6. There they all are. And notice that there is none of these that satisfy our event of rolling a 9. There's no 9 as one of the outcomes. In example 4-9, here we're going to be finding the probability of rolling a number less than 7. So I didn't write that out in words, but that's what that says. Again, there's two ways to kind of think about this. One, you could say this is certain. I am guaranteed to get a number less than 7. So the probability of a certain event guaranteed to happen, 100% going to happen, would be 1. So exactly. The other way that we can kind of think about it might seem like we're saying exactly the same thing. We kind of are, but it really wouldn't be too bad if we said it both ways. So here, the traditional way of doing it. The number of outcomes in our event divided by the number of outcomes in the whole sample space is 6/6. And so that is reducing down as a fraction to 1. So notice here, this outcome satisfies our event, this outcome satisfies our event, all of these outcomes all satisfy our event. And so that is why we have 6 as the number of outcomes that satisfy our event. And that is why we get a probability of 1, because we're simply dividing 6 by itself. And next, we'll discuss complementary events. So the complement of an event is the set of all outcomes that are not included in the event E. So we call this E bar. So that's an E with a bar over it. And that's how we pronounce it, E bar. In example 10, we will go ahead and find the complement of several events. In this first part, part A, they say to find the complement of this event. The event is selecting a month that has 30 days. So the complement of that, the complement would be selecting a month that does not have a total of 30 days, so that has 28 or 31 days. So I always remember the months that have 30 days. 30 days is September, April, June, and November. So there's 4 months. The complement of selecting one of those months would be selecting any of the other 8 months of the year. In part B, it says find the complement of this event, picking a day that begins with S. The complement would be choosing a day that does not start with S. So those are enumerated as Monday, Tuesday, Wednesday, Thursday, Friday. The other 2 days, Saturday, Sunday, those start with S, so we would be selecting everything except those 2 days. In part C, we're rolling 2 dice and adding up the numbers on the 2, right? And the event that we're looking for is to get a sum of 7. The complement of that event would be to get anything except a 7, right? So we have all of the other possibilities, all of the other outcomes, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12. And that would be the complement of the event of rolling a 7. That would just simply be the opposite, rolling anything except a 7. All right, finally, in part D, what is the complement of this event? Choosing a letter of the alphabet, not Y, that is a vowel. So notice there they've ensured that it's going to be well defined because they've said, okay, Y doesn't count as both, right, a vowel and a consonant. So the complement of that event would be picking anything that's not a vowel. So we call those consonants. It's a weird vocab word, not part of this class though, so cool. All right, next, the probability rule for complementary events. To calculate the probability of the complement, E bar, right, we would say that is 1 minus the probability of just E. Or another way to do it is if you know the complement, right, then we take 1 minus the probability of it, and that's the probability of the original event itself. Or yet another way to say it, and all 3 of these equations are equivalent to one another. They are all just rearranged in different ways, but they're all the same equation. The last way to phrase it is that if we add up these 2 probabilities, we should get a total of 1. So one way to kind of visualize this is if we have, as I've drawn here, if we have an event that is some subset of the whole entire set of outcomes, we'll call it E, then the complement of that is everything else in the sample space that is not one of those outcomes. So notice together these make up the entire sample space. And so their probabilities must add up to a total of 1 because E and E bar combined together, that is the set of all outcomes in our total sample space. Okay, in example 4-11, it's not a very fun subject. The subject is on victims of violence. In a study, it was found that 24% of people who are victims of a violent crime were aged 20 to 24. If a person is selected at random, find the probability that the person is younger than 20 or older than 24. Okay, in this situation, the event, E, is that we select this victim and they are within this age range, 20 to 24. All right, they told us 24%. And so the probability of E, that is equivalent to the decimal 0.24. And what we are looking for in this problem is simply what is the probability that they are either younger than 20 or older than 24. So they're not in this range. In other words, we're looking for the probability of the complement of E. And so that's just going to be 1 minus 0.24, and that would be 0.76, or 76%. So 24% of the time, the victim is going to be within the age range 20 to 24, and the other 76% of the time, they're going to be not within that age range. And so that should make perfect sense. Now, we've been talking about nothing but traditional probability theory, and now we're going to move on to empirical probability. The key difference between traditional probability and empirical probability is, in the traditional sense, we say, okay, there's so many possible outcomes, we'll just count them all up, and whatever would satisfy our event, we'll just take those total number of outcomes, divide by the total number within our sample space, and there you go, right? The key difference with empirical probability is empirical probability relies on actual experiences in order to determine the likelihood of events or outcomes. In this next situation that we're going to use for a couple of different examples, we have said, okay, so this researcher, they're interested in what people are going to do in terms of traveling over the Thanksgiving holiday. So they ask 50 people, are you going to drive or fly or take public transportation, a train or a bus? Okay. So with traditional theory, we'd say, okay, there's 3 outcomes. That's our total sample space. And that means 1 out of 3 people are going to drive, 1 out of 3 are going to fly, and 1 out of 3 are going to take public transportation of some form, either a train or a bus. Well, we can't say that because past experience has to come in here. We have to say, hey, not that many people will actually fly, not that many people will actually take a train or a bus. The majority of people are going to drive, right? So the reason that they're asking so many people is so that they can kind of keep a tally of how frequently people drive, fly, or take a train or a bus, and use that information in order to determine the likelihood. So in order to really consider this in an empirical sense, we have to talk about the frequency of these. They asked 50 people, and here is what it broke down as. 41 said they were going to drive, 6 said they were going to fly, and only 3 said they were going to take the train or a bus. There is a total of 50, and these are the individual breakdowns of what mode of transportation people are using. So basically here, since we're using essentially a frequency distribution, we're going to say the probability of our event is the total number of the total frequency for that class divided by the total frequencies in that whole distribution. In this example, 4-12, it says in the travel survey that they just described, find the probability that this person that they select at random will travel by train or bus over the Thanksgiving holiday. So here we're going to be using this formula, P of E equals F divided by N. I covered up the page so I would make myself struggle, make myself remember this. So there were 3 that were going to take the train or a bus, and there were a total of 50 frequencies in that whole distribution. So that was 50. And this, as a decimal, comes out as 0.06, or 6, oh, I almost wrote 3, 6 Here is example 4-13 on distribution of blood types. In a sample of 50 people, 21 had type O blood, 22 had type A blood, 5 had type B blood, and 2 had type AB blood. Set up a frequency distribution and find the following probabilities. So it gives us various different things. All right, so the first thing is I'm going to encode that information that they told us in paragraph form into the form of a frequency distribution. So we're going to talk about the blood type and the frequency for that. Okay, so for type A, B, AB, and O, we had 22, 5, 2, and 21, respectively. There's our total of 50, and we will proceed finding their probabilities that they asked us about. Okay, in part A, they asked us to find the probability a person has type O blood. So I've written that as P of O, and so that is going to be 21 divided by 50. There's 21 people that had type O blood. There's 50 in the total sample space. So that is 0.42, or we could say it's 42%. For part B, they are asking us to determine the probability that a person has type A or type B blood. So I've written this as P of A or B. Now, in order that I don't spend the next 8 minutes having an argument about what the word or means, or what antigens are present in type AB blood, I'm just going to do this the way that we would naturally think about it. So if I need to get type A blood or type B blood, I could say, well, this person has type A or this person has type B. So therefore, there are a total of 27 ways that I would satisfy this event. So I've got 22 people that I could select, or these other 5. If I select any of those 27 people out of 50, that would be satisfying that condition. So 27 over 50 as a fraction, 0.54 as a decimal, or 54%. In part C, they're asking us to find the probability a person has neither type A nor type O blood. So here, that means essentially we don't want type A, we don't want type O. That means they would have to have either B or AB blood. So that is these people, those 7 out of 50 people. So therefore, the probability would be fraction, 7 out of 50, the decimal, 0.14, or 14%. So here, not is indicating the complement, the probability that the person will have type AB blood. There's 2 of those people. There's a total of 50. So we would say they have a 2 out of 50 probability of having type A blood. So therefore, the complement would be all of the people who do not have type A blood, or in other words, the other 48 of those 50 people. And so this is a probability 48 over 50. We could keep it like that as a fraction, or make it 96%, 0.96 or 96%.